Um, and I'm the Executive Officer of Regional Development Australia, Sydney. Firstly, I'd like to acknowledge the traditional custodians of the many lands on which we meet today and pay my respects to elders past, present and emerging. I'm meeting on the lands of the Gadigal people of the Eora Nation. And if you feel like it, put in the chat box what countries you're meeting on today. RDA Sydney is part of a national network of organisations that receive funding from the federal government to basically support the growth and strength of regional economies. RDA Sydney's remit in this charter is really to support our regional New South Wales RDAs in delivering on that charter. The reason why this is the second webinar that we've actually supported around this topic, and the reason why we do that is it presents a local solution to really a worldwide problem. And it also engages the community through an asset that everybody loves. They love swimming pools, they use them and they cherish them. And to actually be able to allow councils to come up with an economically viable solution in delivering something, a technology that has an environmental impact is it's just a good idea. So today, really, we're going to record this session. We're going to have slides. We'll also have a document which basically will cover off on some of the major topics, the major points, and it'll be distributed to all registrants post-webinar. We also are lucky today to have as the moderator Jared Leake, and Jared is the CEO of A2EP. And Jared's had years of experience in trying to navigate industries through alternative energy options and also to come to a pathway that results in really a net zero emissions agenda. So I think you've got the best person in the room to actually moderate this, and I might just hand it over to Jared now and thank him for letting us support this today. Thank you.
Teresa, thank you so much for that lovely introduction, much appreciated. And yes, I'm the CEO of A2EP, and my other credential for supporting today is a swimmer in my youth, spending some 20 hours a week at aquatic centres, so I've known the water side quite well. So yes, A2EP is a non-for-profit organisation. We're funded by members, and we work to improve the energy productivity of Australian businesses. Why energy productivity rather than just energy savings? Well, if you wanted to really focus on energy savings and that's all that mattered, then we'd be swimming in quite a cold pool or a very hot, humid pool that's not very pleasant to be in. We much prefer to talk about energy productivity, and that brings in the value that you create for when you're using that energy. And that means a really comfortable environment that encourages a lot more people to participate at the pool and the aquatic centre and in the community. So today we have a fantastic lineup of speakers. I've had a little skim through the presentations already, and the content is fantastic. Plenty of content here for you today. And just to reiterate, the session is recorded and we'll be sending out the slides for you. And so we're going to take you through what is a heat pump and energy audits are there, and then get down to some really practical feedback for you and lessons learned on people that have been using heat pumps for many years, and also then we start looking forward to the future and new heat pump systems as well. So a fantastic lineup of speakers there for you today. We'd like to kick off today with Alan Pears, who's going to give us our first presentation. Just before I do hand over to Alan, just to let you know that there's the chat box there. If you've got any technical issues, pop that in the chat box. But if you've got any questions, put that in that Q&A and upvote. I think you'll be able to upvote other questions that you may like. And we'll have a few minutes at the end of each presentation to go through those. If we don't get through them, we'll have the speaker try and type in the the responses for you. So keep an eye on that one. Pop those questions in there. We want to keep that really interactive. If we don't get to your question, we will endeavour to have that answered and sent out to you all next week. But please, let's keep it. Let's go for interactive and get those questions ready for us. So yeah, to kick off today, we're going to talk about the heat pump, the technology, and get an understanding of that and the heat flows within an aquatic centre. And with that, we have Alan Pears. Alan is a research fellow at RMIT, and he is also the thought leader for A2EP and has been working with us for many, many years. Alan, I see you brought up the presentation. Thank you for that. And I'll hand over to you now, Alan.
Thanks, Jared, and it's great to be here with everyone. I do have to leave at about 11:45 for another appointment, but I'll be here till then and answering questions on the chat if we don't get to them otherwise. So my job is to kind of give a bit of an introduction and overview of the issues. So here we go. Just looking back, I've been around through most of this time. In the 70s and 80s and 90s, we were kind of focusing on just heating a pool. That was the big challenge, really. And so thermal solar collectors on roofs of aquatic centres and cogeneration plants that produced electricity, and waste heat was used for supplying the heat for the pool. All these were the kinds of things that were being done. But now we're realising that actually this is a complex system. It's got a very complex building, lots of complex equipment, amazing energy flows of all kinds. And as such, we're really looking at a very different picture for the centre, but also we're looking at low-cost rooftop solar, power purchase agreements to buy 100% renewables, councils committing to zero net emissions. All these kinds of factors are now flowing in on us. And there's a few other kind of practical things too. For example, with climate change and with changing expectations, we're finding an increasing need for cooling aquatic centres. We're realising that the condensation problems and corrosion and other issues that are occurring can be avoided if we build thermally better buildings. And as we start to try to use heat pumps in these situations, what we're finding is that a lot of people who historically have basically used gas boilers are having to learn quite a lot of lessons quite quickly because heat pumps are very tricky and are pretty different from a gas boiler. There's also some important differences between indoor and outdoor pools, which I hope to touch on quickly at the end. So let's look at an example of the energy flows in a pool. And you can see the two big things are really about heating the pool water and heating and cooling the pool hall and ventilating it and those things. The rest of the things are relatively small in terms of percentages of the energy, but you need to keep in mind that all of that equipment often is using electricity, which can be quite expensive. So if you're looking at your costs, then those small bits are actually a fair bit bigger than you might realise. So you need to focus on them as well. I won't go through this in detail, but essentially there's lots of energy flows. So we're heating the pool and the building, the hot water. We're cooling and dehumidifying the building. We're using electricity for fans and pumps and appliances and lights and stuff. We've got solar gains coming in through the windows. And through the building fabric if it's hot. And we've got active people giving heat. At the thermal level, looking at the other side, the building fabric often is leaking a lot of heat when it's cold. The hot, humid exhaust air is an enormous amount of energy that's leaving the building. Then people coming in and out are also allowing outside air to come in. And then there's a bit of heat loss to ground as well. So it's quite a complex system. Just to talk a little bit about how a heat pump works to give everyone some common ground. A heat pump is a bit quirky, but of course, all of us have got fridges and reverse cycle air conditioners, which are heat pumps. just to explain it quickly, if we start down the bottom left-hand corner at the cold liquid, this is a cold liquid refrigerant in a pipe. It flows into a thing called the evaporator, and this is a heat exchanger where essentially it extracts heat from the local environment, and that might be from the air or from water or whatever, but it's extracting heat. As it extracts the heat, this liquid evaporates and becomes a gas. Now, this is important because when a liquid evaporates, it absorbs a lot of energy, okay? So when you boil a kettle, once it starts producing steam, the temperature is not changing, but it's absorbing a lot of energy that's making the steam. This low pressure gas then flows to a compressor, which is where we're putting the energy input in, the electricity, and that is compressing it. Now, what happens there? Think about a bike pump. When you pump up the bike tire, you feel the bike pump gets quite hot. Well, that's what we're doing here. We're compressing the gas, but in doing that, we are heating it up. So it's now hot, very hot, high pressure gas. So this gas can now go through another heat exchanger called the condenser, where it can release that useful heat out to the environment. And as it does that, it condenses. And again, when a gas condenses, it releases a lot of heat. So for example, if you get burnt by steam, the steam is condensing on your skin, delivering large amounts of heat to burn your body, right? That's how it works. So then we've taken a lot of heat out. So we've now got a liquid because the gas has condensed, and we run that back through a valve, and then it can just keep going round and round and round. What's interesting about a heat pump too is that it can do both heating and cooling at the same time if you have those two needs. So again, if you think about your fridge is extracting heat from the cabinet to cool the food, but then if you feel the outside of the fridge is actually warming up your kitchen too. So this is the point where we can get two outcomes for one thing. Another important issue that arises is lots of people say, oh, but when it's cold, a heat pump doesn't work. Well, there are situations where you can have what we call icing up problems that do make things a bit complicated, but fundamentally, the laws of thermodynamics work from 0 degrees absolute, or basically the temperature of outer space, which is like minus 273 degrees. So even air at say minus 20 degrees is still very hot compared with outer space, which is where we're going. So what's also important is that unlike resistive electric heating or burning a fuel, a heat pump can be much more efficient than 100% because it's not trying to create heat, it's extracting heat from one place and shifting it to another. So it can be really efficient. Now, one of the things that I hear debated a lot when people are looking at aquatic centres is this issue of how efficient is the heat pump. And this is where the term coefficient of performance comes in. So instead of saying a heat pump is 500% efficient, we say it has a coefficient of performance of 5. That is, we're getting 5 units of heat for each unit of electricity. So that's the key element there. And I'll just show you this now. Sorry, graphs that are. The heat pump's performance varies. It's very sensitive to the temperature difference again across which it's working. And this graph shows us how efficient a heat pump can be. And if you look at the grey line at the top, it says Copcano. That is the theoretical efficiency of a heat pump operating across a temperature difference as shown on the horizontal bar. So in other words, if a theoretically perfect heat pump is operating across a 60-degree temperature difference, its coefficient of performance is right at the top of that graph, it's a coefficient of performance of 7. That's 700% efficient. Of course, real heat pumps aren't that efficient. They're about half of that. But again, there's an important message in this graph, which you can see the smaller the temperature difference that the heat pump works across, the more efficient it is. And once you're starting to get down to quite small temperature differences, like heating water by 20 degrees or 40 degrees, you can see that it is typically running at 400% to 600%, 700% efficient. And that's the sort of space that a pool heat pump should be running in if it's well designed. Now, I should emphasize that the transcritical carbon dioxide refrigerant heat pumps don't quite work this way. They are a bit quirky, and I don't have time to go through them, but they're pretty different, and they need a whole lot of other attention. So another key point is that what this graph is showing is the capacity of a heat pump when it's delivering heat at about 40 degrees. And as you can see, as the temperature gets closer to 40 degrees, which is the outlet temperature, the capacity of the heat pump increases as well. So what this means is that the heat pump can do more. The converse of all this is that if you're allowing a heat pump to run in a really cold environment and you're trying to heat the water up to a high temperature, you will need a much bigger, more expensive heat pump, and you'll save less energy. So these are the key messages from this. Now, we can address a lot of these issues by looking at the exhaust air. And I mentioned the hot, humid exhaust air that's leaving the building. This is an enormously valuable resource because it's got a lot of water vapor in it. And to create that water vapor, every 1 litre of water that's in that vapor form has required about 2.8 megajoules of gas, or about 1/6 of a kilowatt hour of electricity from a heat pump to create as a water vapor instead of liquid in the pool. This is an enormous amount of energy when you've got phenomenal airflows through the building. So this is an energy resource for us. Now, as an example, a New South Wales-based company called AirChange has now developed what they call Pool Pack Plus. And what it does, instead of operating using the ambient air temperature, it uses the energy in the exhaust air as the heat source. So on the left-hand side here, you can see that here's a heat pump operating at about 6 degrees Celsius, pretty cold. And indeed, the temperature of the evaporator in this is -5 degrees, which is a problem because that means the water vapor in the air around it will start to freeze and clog up the heat exchanger, reducing its performance. So this product, you can see in the red box up the top, has a coefficient of performance about 2.7. Now, the Pool Pack Plus draws in the hot, humid air, condenses the water out of that and recovers that energy from the condensing of the water, and it runs at a much warmer temperature, so it doesn't get icing up. And as you can see up at the top there, the coefficient of performance is now 4.1, which is 50% better than the COP of 2.7. So this is how we can maximize the benefit of our heat pump. Another important thing about this is that the way the energy recovery from waste heat goes shows that you're actually saving most of the energy when it's colder in winter. Now, this is good for 2 reasons. One is if you're relying on rooftop solar is actually nowhere near as plentiful in winter as it is in summer. So if you're saving most of it here, that's actually helping fit with your situation with your PV. The other thing is that particularly in the southern parts of Australia, we're looking at winter gas shortages in the next few years. And that means we are looking at higher prices for gas and more concerns about the availability of it. So these are good reasons why the characteristics of this heat recovery system and of a heat pump are really good. They are fitting our new renewable energy sources very well, solving our problems with gas and reducing the energy consumption. This is pretty much my last slide. I'm sorry, I'm going a little over here. What I've tried to do here is just focus on the building itself, because a good performing building is really important. What I've done here is take a very simplified box with some glass and look at the energy flows through the roof and the walls and the glass at 3 different temperatures. So we've got 5 degrees, cold day or cold night, 20 degrees, moderate, 40 degrees, hot summer. And what we see on in the left-hand graph is that the poorly insulated building uses enormously more energy to keep it comfortable than the efficient ones. They can all benefit from solar gain at the right times as well. I should say the right-hand example is essentially the efficient building, but with half as much glass as the other one. At 20 degrees, of course, the scale is different, so the amounts of energy flowing are much smaller. But again, the insulated with low E double glazing building is performing far better, using a lot less energy, providing much better comfort. And in fact, in this case, there'll be times where you might want to cool the building because the amount of solar gain will be outweighing the losses from the building. Again, this is where when you're getting these really good buildings, you need very good shading. Then the last example is just at a really high temperature of 40-degree day. And here we see the poorly insulated, highly glazed building has got massive loads to try and cool. And you'll be paying a lot of money and you'll be struggling to keep that building comfortable. Now, my last quick slide is just to raise the issue of outdoor pools. Outdoor pools are incredibly sensitive to wind speed. And you really need to do everything you can to protect it from the wind. Also, the hotter it is, the more water is evaporating and the more heat is being lost. So again, you have to be very careful about temperature management and things like that. And I'll stop there. And that's just my cute picture of the difference between a low emissivity window that's lovely and comfortable and a less good window that's covered in condensation and making you feel really cold. Thank you.
Alan, thank you so much. A really good introduction to the technologies and the issues there. Wonderful, thank you. And just to remind everyone, throw those questions in that Q&A box and we'll get to those. We've got time, a couple of minutes to take a question. And if we don't get to that now, Alan will hopefully type in a question before he has to head off today. So I'll look out for any questions that come through there. Meanwhile, Alan, I've got one for you. In terms of heat recovery, we often hear about a thermal wheel being used. And I see multiple claims, and whether it be on YouTube videos or vendors saying that, yeah, our thermal wheel has an efficiency of 80, 90+%. But from our understanding, that's really sort of cheating or losing a lot of the story there. Could you explain just quickly the difference between that thermal wheel operation versus what we saw today from that Pool Pack Plus?
Yeah, so a thermal wheel is basically a wheel, and half of it is exposed to the air leaving the building, and the other half of it is exposed to air coming into the building. And it has usually a very thin film that's sort of a spiral, providing lots of surface area. So the theory is that this spiral of film will absorb energy from the outgoing air and then as the wheel goes round, it will transfer it to the air that's coming in. And yes, they work, but as Jared kind of suggested, the problem is they don't work all that well all the time under all conditions. And that's where you face real problems, because a lot of the specifications are not really typical conditions or don't model over the whole range of circumstances your facility will face. And I guess that's where what we see with the heat pump is that literally you are able to condense all of that water vapor, which is the majority of the energy in the exhaust air. It's not actually the hot air, it's the water vapor. So getting that condensation happening is really important. And look, you end up with a lot of liquid water, which can be handy as well. Yeah, I guess, does that explain it enough?
I think so. I think we probably need some numbers to refer to say a thermal wheel, the efficiency of that would say really at maximum, because it doesn't capture that latent heat, it must be 10, 20% really. That's the best it can ever do. If you get latent heat, okay, now you're talking 80, 90% efficiency. So thanks, Alan. I've got a question here about backup options for heat pumps, and we've talked about this in the past, and we think you shouldn't need a backup if the system is designed and maintained correctly. Very high availability you should expect from a heat pump system, very much like industrial refrigeration systems, well into the high 90s of availability and reliability. Any thoughts on backup?
Yeah, well, I think again, one reason why a lot of people keep specifying backup is because they are not utilising the waste heat from the exhaust air. And so, as I said, if your heat pump is trying to heat your pool when it's 5 degrees outside, it will be suffering icing up, and it will be working across a big temperature difference. So its heat output capacity will be reduced, right? Yeah. So that's one reason why a lot of people think about backup ones. And I guess the second issue is really about the reliability. And as Jared has said, I mean, if you go into any large commercial building, they're all using large heat pumps, but they're using them for cooling and dumping all the heat out through the other side instead of using it. So in that sense, these are very reliable pieces of equipment, as long as they're not losing refrigerant. And a modern heat pump should have real-time monitoring of refrigerant, to be blunt, because when you lose refrigerant, not only are you potentially impacting on climate change, but you are undermining the efficiency of your unit, because a heat pump with not enough refrigerant runs less efficiently and has less capacity as well. So you need to make sure you don't lose the refrigerant. Once you've got that, you've got a very reliable thing. The average fridge, how long does that last? I can't remember how old mine is. So again, also, if you are concerned, you can have 2 heat pumps so that you've got some capacity if you need it. But again, that starts to increase costs and issues like that.
Indeed, and I think we've got, there may be some specification issues we need to get to if it's going to be, the heat pump's going to be sitting in the plant room with a chlorine type environment and corrosion of the equipment there. But that's specifications is a whole other discussion. I'm just going to try and tick off a couple of questions there. There's questions on recommended for engineering companies. We'll send that out afterwards. There is a couple that are looking very progressive and seem to understand the idea of this heat recovery and what have you, a couple of consultants there. And we'll send the details of those out that we see that are more progressive types. There's a question regarding chloramines and corrosion. Well, there's plenty of history now. That the one you mentioned there, Alan, of Ride, they've had a heat recovery unit in there for 20 years. It's not as good as the new system that's gone in, but it certainly has been dealing with chloramines for 20 years. And the plastic, the painting and the coating that they put on the fins there certainly allows that to last that 20 years, and also on the insides of the system as well. So it's pretty well known of how to handle those chloramines and make sure that corrosion is not an issue. Alan, many thanks. I know you're only on here for another 10 or 15 minutes. Feel free, if there's some more questions come through, and type in some answers, please go for it.
I'll look at the chat.
We'll go to our next speaker. Today, next we're going to talk about auditing and white certificate schemes available for aquatic centres. And I'd like to introduce to you Trent Hawkins. Trent, if you could bring up your presentation and start sharing for that one, we'll dive into your presentation. Trent Hawkins works for Northgordon. He's their regional operations manager and been in the energy consulting industry for many years. And Northgordon has done many audits for aquatic centres and really knows the ins and outs very well. And this is one of those engineering companies we'd certainly recommend that understands the heat flows for an aquatic centre extremely well. Trent, I'll hand over to you and start the presentation, please.
Thanks, Jared. Thanks for the introduction, and thanks, Alan, for explaining some challenging, complex issues like water coefficient performance is and how the heat pumps operate. So I don't have to deal with that. I can just talk about more general things around, I guess, looking at areas of energy efficiency improvement in aquatic centres and also some of the a bit of an overview of some of the heating systems in place. Just this thing to move on. Yeah, so just very quickly, Northgordon, leading energy and carbon consultancy that works mainly with industrial and large commercial businesses. Tend to work more in the sort of complex thermal energy systems rather than just typical commercial buildings. So aquatic centres has been an area of focus for us. And I think I'm not sure exactly the number, but we've probably audited in the range of 10 to 15 aquatic centres in the last few years. So we've got a lot of experience there and also understand heat pumps and how to design a suitable heat pump system for to replace other heat applications in industrial and large commercial facilities. And just to explain, so I guess there is a bit of a combination of areas that we can offer support in, including the typical areas around feasibility studies, energy auditing, engineering as well. We have the ability to help businesses put their strategy together around energy and carbon management, and also alternative options around procurement of energy, such as renewable energy. And I guess the last key piece here is, which I will talk about, is certificate funding opportunities. So through things like the Energy Savings Scheme and the Victorian Energy Upgrades Program, we help businesses access funding through those as well, particularly looking at what's called measurement verification, which I'll explain a little bit in a moment. So yeah, look, as alluded to by Jared, Northgordon has recently conducted a number of energy audits for some central New South Wales Council aquatic centres, and then prior to that, other audits for a number of other councils as well, primarily in New South Wales, although we've done some work for Victorian aquatic centres as well. Just drawing some key observations from that, from those recent audits and our general experience. I wanted to point to some of the things that probably well known to everyone here on this webinar, but worth stating clearly. And the first of those is that pools are a vital asset to the community. There's a high need to have them operate and function and deliver the service to the community. And often, financing projects can be challenging, especially where they're high capital cost. So that there are limits to challenges, I guess, for councils and other aquatic centre operators to invest in some of these technologies. And one of the things we've identified is that there is split incentive where you might have a council owner of an aquatic centre, but there's a third-party operator, and effectively the third-party operator may be paying the energy bills, but it's the council-owned asset, and that they would be the ones who would need to invest in new equipment, for example, and they will be paying a fixed price for the operation, to the operator to run that facility. And as actually Alan alluded to, there is a big variance in energy consumption and also technology that's used between your sort of annually operated large recreational centres and your more regional seasonal pools, that may only run for a few months in summer. And in our experience, in aquatic centres, often there are a number of energy systems that are not well optimised. And that can be caused by a number of factors. One is that you need to maintain the hygiene levels in the pool, the performance of the pool from a hygiene point of view, and the energy efficiency can sometimes compete against that. And having people who understand well how to optimise those systems is necessary. And look, this is just another version of I guess, a heat flow diagram compared to showing what Alan put forward before. And I won't go into too much detail here, but there are a number of different energy using systems in an aquatic centre. You have the pool itself, which in most cases is heated, actively heated, and you'll have a pool water system, a loop of pool water that's driven through a filtration system, whether it's sand filters or ultrafine filters. There's a level of sort of cleaning up that water, and then the wastewater that is removed from that process, where there's backwashing as well. And then you have usually a separate heating loop in place, which actually your gas boilers or your heat pump is attached to, and that's supplying heat into that heating loop, which heats the pool to the required temperature. And then you have chlorination, UV, and other forms of disinfection as well. The water. So there's different energy systems. So you've got pumping in there, as well as the actual the heat source that's being supplied. And then in the pool itself, you've got a range of different areas of areas where heat is lost. So whether through the ground, through direct radiation, through convection, the air, but mostly through evaporation of the water coming off of the pool surface. And then as Alan alluded to as well, you have to actively condition that space. You are removing your air and bringing in fresh air. You might be cooling that air down or heating it up, depending on the seasonal situation, but usually cooling it down. And then you have to dehumidify that air as well. And you might have heat loss through glass and other, through the building fabric itself. And yeah, just, I guess, looking at, before we talk about heat pumps, there are, and the large heating systems, and this is some of the insights we gleaned from those recent energy audits. Yeah, there are a number of low cost or more obvious energy saving opportunities to apply, or commonly applicable opportunities that can be applied in aquatic centres. One of those is to deal with pumps, recirculation pumps running through filtration systems. It's quite common to find pumps running on fixed speeds and the actual flow rates being throttled with a valve that's manually operated, which is a very inefficient way of reducing the flow rate on those pumps. You're better off actually putting a variable speed drive in place and directly controlling the output of the pump according to the level of circulation you need. We're still seeing a lot of facilities where they haven't done an LED lighting upgrade, and there is opportunity there. Very low cost these days to replace your old T8 lighting, and other forms of inefficient halogen lighting, etc., with LED. Behavioural is really another obvious choice. So just ensuring that equipment is operated efficiently and not run for longer than it's required. And I'll talk to this one in a second. But
just wanted to let you know we're running a little bit short and ask you just to tap the accelerator a little bit there for us, please.
All right. And then the heat pumps as well. and I'll just jump over this one, then I've pretty much covered that in the previous one. But so just looking at heat pumps, like, well, the question of the source of heating that for the pool itself, there are a number of different technologies already in place. All of these are in pools in some form. So you've got gas boilers, you've got the heat pumps referred to, some have biomass boilers, solar thermals in place, as well as gas-fired cogeneration. So to compare the different technologies, this graph is, just really tables really representing some of the key differences between those technologies. So the overall efficiency, Alan explained what the coefficient of performance was, but you could view that as 400% for a heat pump. And then the different efficiencies of the system, looking at a set of energy prices that are on the right there and the emissions factors that are presented. Each of those technologies show what the net outcome is. So what's the overall cost, the greenhouse gas and emissions, and the level of maintenance costs that's required. You'll note here that a heat pump is showing as having a relatively high emissions, but it is still lower than gas boiler. Important to note there, though, is that that's only on today's emissions factor, and based on all of the predictions, the grid electricity factor is heading south very quickly, and that number will turn, and within a few years will become the lowest emission source of heating that's available. And we can, if people have any questions about the information in this table, they can raise it in the chat as well. So, some of the pros and cons, gas boilers are widely used technology, do have a wide operating range, but there is a low efficiency of energy conversion there as well. Heat pumps, same, they've been in use in aquatic centres for decades. And there are many that are still functioning today that were installed 20 years ago. But they do require a heat source, but the ambient air is a readily available source of heat. Biomass boilers are an opportunity as well, but there are challenges around getting a long-term reliable contract for fuel supply. And solar thermal is also another great option, but generally can't be used as the sole source of heat, particularly where you've got an all-year-round pool, so you do need alternative sources. And cogeneration has been around for some time, but there are issues around compatibility with other heating systems and solar PV, particularly where there are constraints on the amount of export to the grid that's allowed. And it's less attractive as the electricity grid decarbonises. You effectively lock in a source of energy to the pool, which will be running on fossil fuel supply. This was thankfully covered off mostly previously, but just to note a few things to consider. First is that you do need good design integration for successful implementation of heat pumps. Wrongly installed heat pumps may lead to additional icing than otherwise would be necessary. There is a really good opportunity to also consider removing intermediate heating loops. So if you look at that diagram on the right there, you've got pool water coming in through a heat exchanger and being heated from a separate loop that's supplied from a heat pump. An alternative configuration, if your heat pump is able to accommodate it, is you can actually directly heat the pool water itself from the heat pump. We did do a business case for a Sydney Aquatic Centre a couple of years ago, and this was actually including using a coil in the ventilation system to extract more heat. And there was a 600 kilowatt heat pump that was proposed. Just to give you some numbers there, so the payback was in the range of 8.6 years at that time. Just conscious of time, and I just wanted to finish on these last couple of slides about certificate funding. So there are a few different schemes in Victoria and New South Wales where councils and other businesses can access funding for equipment upgrades and energy efficiency projects. These are some of them, the most applicable one. So in the New South Wales Energy Saving Scheme, you've got the Project Impact Assessment Measurement Verification Method, which uses measurement verification approaches. So you're comparing a baseline operating performance, a baseline performance of a system with a actual operating performance of a system, and assessing the difference between the two and the actual energy savings that result. Can explain that more in further detail if needed later, but it allows you to forward create for 10 years. And there's a similar scheme in Victoria as well called the project-based activities. Then you do have some deemed method as well. So the Victorian energy upgrades, there's the water heating and space heating and cooling activities. But at this stage, there are still limited opportunities for replacing or converting from gas to electricity where it's using a heat pump. Just realizing I'm running out of time, but this is a graph of some of the certificate prices. We've got, there's been a lot of growth in the Victorian energy efficiency certificate prices, and that's risen from a low of $40 only about a year ago up to now it's about $75 certificate. So it is a really great source of funding for those pools that are in Victoria, and then some of the other certificates, including the Australian carbon credit units as well, which is another option. Yeah, and just lastly, we recently completed we recently helped an aquatic centre in Victoria with a BMS upgrade, accessing certificate funding through the project-based assessment method within the Victorian Energy Upgrades program. And that project itself involved upgrading some digital controls and sensors and allowing better control of HVAC fan speeds. And that project was able to create 2,000 VEECs, which at the end of the day was worth of over $100,000 worth of revenue to the council. So yeah, if you want to find out more information, there is the Energy Efficient Water Heating Technology Guide for Aquatic Centres, the New South Wales Government released a couple of years ago, and Northgordon was involved in preparing that guide. And I'll leave it there.
Very good. Many thanks, Trent. And I think you see that's quite a complex navigation between all these funding systems and what have you. But thanks for giving that overview there. I also appreciated your comment about these VSDs on the filtration pumps with valves used for reducing flows and adjusting flows. I've heard that put another way. It's like driving your car where you'd have your foot on the accelerator full the whole time and you control the speed by just using the brake. That's what's happened with if you don't have that VSD. So good to see that recommendation. Good one. Trent, many thanks for your presentation. We're going to move on now to Ian Garrod from North Sydney Council, working with North Sydney. I'm just going to share the presentation from my screen on this one. Just bear with me. And Ian, that should come up for you.
Thank you.
Very good. Ian, as the Sustainability Project Officer for North Sydney Pool, great to have you here, and you've got some fantastic experience over the last few years of a transition from cogen and boilers to heat pumps, and so I'll let you take it away and look forward to your presentation. Thank you, Ian.
Yeah, thanks, Jared. And also to Alan and Trent has been some great background information that will be useful in understanding what goes on with this here too. Yeah, look, North Sydney has been a great place to find out how the different technology works. The most recent upgrade of the pool was in 2002, and that's when the heat pumps went in. Previous to that, there were gas boilers. And at the same time the heat pumps went in, also solar thermal panels were put on the roof. So that's what you can see there on the northernmost building. That's solar thermal panels, or just normal solar hot water panels, I guess a lot of people would refer those to as. And they've been good. They've been lasting quite well, very low maintenance. But anyway, let's move on. Thanks, Jared. So the pool originally opened in 1936, and since 2002, this is what we've had: heat pumps, gas boilers, flat panel, solar, hot water and cogen. So with this mix of energy systems, what was the best version of heating to use? What was the most appropriate? What was the lowest emissions? What was the most efficient use? What was the lowest cost? And so just as a background, the 3 units of heat pumps here, it was 250 kilowatts of electrical input and 1,000 kilowatts of output of heat. Very efficient. And that's when you look at the gas boiler just below, there's 1,370 kilowatts of equivalent energy input, and you only get about the same amount of heat output. So that in itself is a really good illustration of just how efficient heat pumps are. The flat panel solar hot water system was around about 100 kilowatts. The documentation wasn't around recently. We lost that many years ago. But we think that the output was around 100 kilowatts, and it was a substantial amount of heat. And it was generally used as a preheat for the pool. So it was also very low cost heat. So that was always utilised whenever the heating was required. And in Sydney, right next to the harbour, the pool didn't really need any heating because in the summertime, because there was just so much ambient heat. In fact, the pool got too hot for some people in the summertime. So there were issues. Cogeneration, we've had that since 2014. That was installed at a time when gas was actually quite low cost. But since that was installed, the prices of gas have skyrocketed. So yeah, it was interesting to find out what the best systems to use would be, or how to prioritise the control of those systems. Next, please, Jared. So this is what led us to get an energy audit, which we got in 2016, 2017. That's what we're after. Yeah, and it's very complicated, really. Pool management, understandably, is very, very careful about keeping the user conditions within a very narrow band of tolerance. The letters come thick and fast if the temperature gets too hot or too cold. So that's a very critical point. So we wanted to find out what would be the best operational regime with a diverse heating equipment. And the learnings would help inform the design of the new pool. Next, thanks. So coincidentally, it was Northgordon prior to Trent who did the energy audit on our pool. And this is some of the things that we found in terms of the cost comparison and emissions comparison with electricity generation in dollars a gigajoule when using the cogen system. So you can see the marginal cost, meaning just the actual cost of the electricity, not including the cost of capital. The grid import electricity was cheaper than the cogen if there was no heat recovered, and slightly more expensive than the cogen with recovered heat. And interestingly, to have the break-even point for when electricity became cheaper with the cogen system, you needed to be able to utilise 80% of the heat from the cogen system to make it worthwhile to run in terms of cost. So in North Sydney, we only needed the cogen to be running at 80% or more of recovered heat for about 3 months of the year. So it wasn't great, wasn't well suited to North Sydney. And so in this case here, we had back then we had 50% green power, and that was at a premium of 5.3 cents a kilowatt hour on top of just standard grid power or black power. So you can see that even with that extra premium, grid imported power was still very cost competitive with cogen with full heat recovery. And since 2016, electricity has become cheaper and cleaner, and it looks like it's going to become, as Trent mentioned, much cleaner over time. In fact, North Sydney Council has just signed up for the contract for 100% renewable energy from 2023, Christmas 2023. So only a year away, Christmas 2022 actually it is, so it won't be long. And so it'll be far cleaner, zero emissions from the electrical equipment, including heat pumps. Next please. And so this is the cost comparison and emissions comparison for heat generation as compared to electricity generation from cogen. And this also includes the gas boiler too. So very clearly there you can see that the marginal cost was cheaper with a cogen because heat is a waste product from the cogeneration system. When you use a heat pump, half the cost of gas, and much cleaner than gas, even with 50% green power in the mix. Yeah, and as I said before, solar hot water system was difficult to calculate exactly, but was the cheapest and low emissions, although not a major contributor, but still a worthwhile system at the time. Let's look at the next slide, please. Pool energy trends pre-cogen 20. Yeah, so this was interesting. So this data comes from Agility, and they do a lot of council energy performance measurement and billing aggregation work for councils across the country. So it's a great source of energy information, and so we looked back at how things went from the point when we installed the cogeneration system, and looked at the next 5 years. So from 2013-14, that's essentially pre-cogen. Straight away after the cogeneration system went in, the cost of energy from the pool increased by around about $76,000, and the energy increase was 4,700 gigajoules. So it's a huge jump. And the next year, it's when we started looking at the next year after 2015, once we saw the figures, we said, let's look at an energy audit, and straight away we started to claw back the costs down to we started to save around about $77,000 a year once we fully implemented the recommendations of the energy audit. But we could never get the energy consumption back down. So as we can see there, the cogen system caused a large energy increase. And we compared that chart with another building, which is council chambers, and we could see then that it wasn't the extra energy cost was nothing to do with the weather or the climate. Thanks, Jared. Next one, please. So this is what we found out when having a close look at the cogen system based on the high consumption. And here's the quote. Essentially, if the council turned off the cogeneration system, it would generate the following savings. It would save 80 tonnes of carbon dioxide equivalent per year, $20,000 a year of cost savings, and 4,800 gigajoules a year of energy savings. So we could see pretty well straight away it was time to stop using the cogen system willy-nilly, which it was actually running permanently before that time. And so then after that, we've only been running the cogeneration system at times when we need a lot of heat and at peak periods. So when the cost of electricity had a potential to spike high, and also to minimise the capacity charges. So by really changing the control regime of the pool equipment, we could make some significant savings. But overall, we could see that generally it wasn't a good system to have. anymore, certainly anymore, because the cost of gas had gone up so much since we installed it. Thanks, Jared. Okay, other lessons. So the ideal operational regime that we found was to run the solar thermal first, cheapest and cleanest, the heat pumps, next cheapest and cleanest, the cogen, which we only used when we really needed the heat, like in the depths of winter, and the gas boilers last because it was so expensive. So in reality, we found that it was very difficult juggling the equipment because, you know, all of the equipment was very old by the stage we got the energy audit done. The heat pumps reaching the end of their typical technical life. That's one of the heat pumps in the photo there. Not a glamorous looking piece of equipment. It's fairly decrepit, and inside it was a number of the heat pump units had broken down by that stage. So it was a matter of nursing them along. The gas boilers, they had some issues, less frequently because they were much simpler forms of equipment. The cogen was quite expensive to look after as well. And just the other point there, which is critical about running a pool in terms of cost of operation, it's really important to keep the electrical demand to a minimum, especially between the peak periods, which has been 2 p.m. to 8 p.m. in New South Wales on weekdays. So by having demand control, we saved around about $20,000 a year once we got the demand under 250 kilowatts. And so that's one thing that you can do quite easily with a large body of water. You can use the body of water as a thermal mass, a large heat mass, and the temperature goes down relatively slowly. So if you want to heat the pool in the morning before the electricity becomes expensive, it's a great thing to do if need be. And then you can turn the heat pumps off during the expensive time and turn them back on again to start reheating the pool once the pool temperature starts to drop a bit. But demand control was something we found is very, very good to implement at very low cost because we already had a BMS system in place. Thanks, Jared. So for the new pool, the most recent specification, this is what the equipment in general will be. 3 water source heat pumps. So we're maintaining water to water heat sources. As you can see, Sydney Harbour is right next to the pool. The heat is actually harvested from the harbour water rather than the air. I think that's mainly to do with the large heat capacity that water has. A slightly more expensive setup, I understand, but when you've got very efficient, very large mass of heat in the harbour next door, that's the most effective most effective heat source. So we'll also be using solar hot water, but not straight solar thermal panels as previous. What we'll be using is a backing panel. So this is called a PVT, or a photovoltaic/thermal backing panel. It's a water-filled aluminium jacket affixed to the back part of the backside of the solar PV panel. And the idea is to cool the PV panel while heating the water. And so there's dual benefits there because a cool solar panel generates more electricity. So that's going to be very interesting to see how that works out. But from the modelling, the savings should be significant by the look of it. In terms of backup heating, the engineers have said that the gas boiler is unlikely to be called on. But because we've already got the gas boiler, why not keep it in there just in case it is required? So that's going to be retained. And I think, you know, to be fair, like with great respect to the pool management in the past, the pool managers have always had gas. You know, everyone's familiar with using gas, and there's a bit of nervousness about not having gas as a heating method in a pool, because we just don't really know, if it's okay to go without gas, essentially. So it's been interesting going through the process of looking at risk management, and retaining the gas boilers is a great method of risk management. Perhaps it won't be used at all after a few years. We might look back and say, well, we don't even need the gas boiler. Let's see. Electric reverse cycle air conditioning for the space heating and cooling. Previously, it was all gas boiler heating. So it's good to see the gas not involved in the space heating. Hot water for showers will be from a CO2 heat pump. And electricity, solar electricity, initially a 120 kilowatt system. We've got space allocated for a battery electricity storage. So that will hopefully be installed once more money becomes available. And grid electricity, 100% renewable from 2023. That's the aim. Thanks, Jared. So initial intentions were to have an ammonia heat pump, and also to utilise refrigerants that had a 0G global warming potential. So more information would be great about the upfront costs and how can we mitigate the upfront costs. So energy saving certificates would be a great help, but we understand that to access energy saving certificates, we wouldn't be able to carry on with the gas heating system. So perhaps there's a bit of time to look at that before implementation. Bigger PV system over time. So we're looking forward to being able to expand that system. At the moment, it looks like there'll be insufficient PV to operate all of the heat pumps simultaneously during the winter when when the power's most needed. But in the summertime, there'll be plenty of PV available, more than likely exporting some of the power back to the grid. Thanks, Jared. Just go back to that. Go back to that one there. Yeah. So this was interesting because we knew that there was a CO2 heat pump available for domestic hot water that a lot of hotels and what have you had been using for a while. The engineers did a cost benefit to compare the cost of this heat pump compared to gas boilers, and found out that the heat pump would recover its cost premium within 5 years. So yeah, it's great. It's great to have that in the system. Yeah, and just going back to that one too, just to reiterate the issue about solar electricity. Rooftop solar is about a third of the cost of grid power. So those sums are worked out using grid power. So the cost of the time to recover the cost, the extra cost will be significantly shorter than modelled. Next, please. Just drilling into the solar hot water. So this is roughly how, just a diagram of how the solar thermal backing panel works. So that picture there is just looking at the rear side of a PV panel, and the two bars going across the panel, or three actually there is, they'll be clipping the cool sheet or the aluminium wafer to the back of the PV panel. So there'll be direct heat transfer through the panel into this backing panel, which is filled with water. Water comes inside one side and out the other, heated up. So this will be very interesting to see how that goes. And I understand the University of New South Wales are keen to get data on the performance of those backing panels as well. So there's some great analysis coming out of that. Thanks, Jared. Yeah, so, I think a lot of people are aware of this. It's easy to stick with things that are familiar. Yeah, more more information would be great to have for all of the personnel involved in energy systems generally. Yeah, so I think that's all fairly self-explanatory. Next, please, Jared. Plenty of ambient heat available for heat pumps. So, thanks.
Good one. Many thanks, Ian. There sure is plenty of heat available there. Ian, great presentation and great to see the technology, but new technology, some innovation happening there. And we'll be watching that, how that PVT goes, and looking forward to hearing about more results on that as we go forward. We're a bit short on time, Ian, but there's some questions in the chat box and the Q&A. If you're able to, feel free to type in a few answers there. You go for it. I think we've got some others typing in answers as well. So with that, we'll move forward and get on to Ross Kingston, talk about Brimbank. Ross was joined us last year in our Aquatic Centre presentation, telling us about the project there. Now, 12 months down the track, great to get an update from Ross. Ross, if you're able to, share your slides, or was I going to share your slides on this one?
Yeah, I can share if that's all right, Jared.
Yeah, go for it, Ross, and tell us about how things are going with St Albans project.
Yeah, great. I'll get to that in a sec. Can everyone?
Yeah, that's come through for us, Ross. Go for it.
Great. I'd just like to start out by acknowledging and presenting today from the lands of the Bunurong people in Melbourne, and pay my respects to their elders, past, present, and emerging. Which for me is always a pertinent point when we're talking about issues of gas, which in Australia is still primarily extracted from unceded lands of traditional owners throughout the country. But yeah, my name's, and thanks also, to the Alliance for Energy Productivity and Regional Development Australia for having me today to present. It's a really big passion of mine, and really excited to present. I'm really excited about all the developments that are occurring in aquatic centres and local government facilities more generally, regarding the transition to what we call at Brimbank electrifying everything. By way of introduction, so Brimbank City Council is in the northwest of Melbourne. And we've currently got a new aquatic centre under construction that will be in St Albans. It's a redevelopment of an existing, much older centre from the 60s into a much more larger and better facility. It'll be called the Brimbank Aquatic and Wellness Centre, so it'll be incorporating a lot of community services and wellbeing services in addition to the leisure centre aspects. So quite a large facility. It'll be an all-electric facility powered by on and off-site renewable energy. So it'll also be 100% it'll be zero emissions in that respect. So I did present about a year ago. The update today I can sort of present on is we've now finalised the design, so I can talk a bit more definitively about that design that we've finalised and some of the design considerations that we grappled with in getting to our final design. So this presentation is probably sort of looking at the issues once you've decided to go all electric and do away with gas. Some of the considerations you'll be looking at in terms of building a new facility. There are, some quite difficult and more challenging considerations perhaps in retrofit projects, which Ian's really great. It's really interesting to hear about. But this is a new facility, so we're talking about it from that kind of perspective. And this is really the short story of how we got to that decision to go all electric. I mean, there's a longer story too about some of the strategic objectives Council has around climate change, but in the interest of time, I won't go through those. But just look, this graph's probably already been presented a few times today, just in different iterations. It's really just the the energy footprint of looking at a gas-based heating system moving to a heat pump-based system. I mean, looking at this, I better go through the graph to try and explain, but I mean, I just don't understand if you're setting out to build a new aquatic centre today, why you wouldn't be going all electric, to be honest. But what this is essentially showing is the energy footprint of the whole of the facility. So the heating and cooling component and what we call like the other parts of the building, the appliances, the lighting, etc. And these were sort of the three scenarios that we looked at in sort of understanding that, like the economic kind of proposition that we were getting into when we asked the centre to design without gas. And yeah, it's already been gone through today, but just the coefficient of performance of electric heat pump systems is so much greater. So when you look at the actual net energy consumption, you're looking at a much reduced energy consumption. So on the left-hand side, we've got what the gas boiler-based business as usual system design was looking like, because we benchmarked the business as usual design approach throughout our design process. And yes, look, I mean, cheap gas is gone. So the whole, you could say, oh, well, you know, there's price differentials between the unit of gas and electricity, but that's quickly a receding thing into history. So the two columns on the left-hand side are just like the net energy footprints of the two different scenarios, the gas boiler-based heating system with a separate chiller for cooling, and our heat pump-based heating and cooling system for the whole facility in the middle. And then once we've applied a 500 kilowatt PV system, we are able to estimate annual savings of around $200,000 compared to the business as usual system. Gas-based system, yes, you could apply a 500 kilowatt solar PV system to the business as usual scenario, and that will deliver considerable savings as well. But that 200,000. So some of that savings is made up by the solar PV system, but a good portion, about 40% of it, is through the actual savings achieved through the different technology for heating and cooling. With the column on the right-hand side, you can see that that red perforated square is the additional the self-consumption by the solar, and the very tiny little blue perforated line is the solar export. So it's a high proportion of self-consumption of the solar, and we've been able to achieve that for a thermal energy storage system, which I'll talk to in a bit more detail on a different slide.
Ross, sorry to interrupt there. You made a change on the top left there a second ago, and that seems to have chopped the slides, certainly from my view.
Okay.
You want to change that back? Yeah, that's better. We can see the whole slide. And we're just running a little bit short in time. If I could ask you to speed up just so we finish in 5 minutes or so.
Yeah, no worries. This has already been alluded to, but before setting out to do all electric heating and cooling systems, you're not going to be getting anywhere if you don't start off with a high performance building envelope. So this particular project had R&U values for the walls and windows specified well above minimum code requirements, which are woeful anyway, but we went well above. We've got airtightness testing occurring during construction to ensure the integrity of the construction process, and we're getting what we paid for. And we, of course, have got heat recovery systems and an optimized pool hall air handling unit system applied to both the pool hall, but also pools have backwash water that go into a tank. We're recovering the heat from there as well, and reincorporating it into the cycle. Yeah, in the interest that there is, and Alan and some others that have presented today sort of alluded to it, there is the possibility of using recovered heat to boost the efficiency of heat pump performance. We haven't gone for that approach in this instance, but as Jared and others have alluded to, it's a very promising area to look at in heat pump designs for aquatic centres, and want to encourage all to sort of consider in their own projects. Not necessarily a counter to that, but probably the only consideration in what we were doing is we have a system in our pool hall that is it's sort of like an air pressurization system. So it's supposed to reduce humidity in the pool hall as an objective of the system as well. So reducing some of that latent heat that's available. Anyway, in theory, but that's the theory, and that was just one of the considerations around why we didn't go with the recovering heat to boost the temperature of the heat pump system. There were some other cost considerations involved as well. But yeah, a very, very important area of investigation and consideration. This is just some design pictures which I thought I'd use to maybe explain how our system's working in a little bit more detail. So we've got what's called a 4-pipe heat pump system, which is a simultaneous heating and cooling system. Meaning that it's an air to water heat pump, but its primary heat source actually for the heating is when there's a cooling load is the waste heat coming off the cooling load circuit. That's the when the heat demand surpasses what's available from the cooling side, it does source heat from the air, but that's just a quirk of the system that we've got. It's a simultaneous heating and cooling system, and you can achieve some really high COPs, particularly when there's the simultaneous heating and cooling demand. On top of that, so we've got the thermal energy storage system, and we've got a 500 kilowatt solar PV system. So one of the design objectives of what we've done is to try and, because we knew we had such a large solar PV system, and every centre should be trying to maximise your solar PV because it's just a no-brainer and a very low-cost form of energy and low-carbon electricity supply, obviously. So knowing that we had that, what we've attempted to do is try and utilise that to its maximum and reduce utilisation of the heat pumps out of solar PV generation hours, and that's where the thermal energy storage tanks come into play. When the solar PV is generating, and there's excess solar generation, the thermal energy storage tanks will call a demand and will be heated. They'll be charged, and then they can be discharged after the daylight hours, and instead of using the heat pumps or minimising the use of heat pumps outside of solar PV generation hours. There's a few benefits in that. Because I think this might have already been mentioned, but the heat pumps, they like to be utilised depending on how they're sized, like they want to be utilised at around 70 to 80% of their capacity. That's their optimum efficiency. And so by adding sort of an additional demand during the solar PV generation hours, we're increasing the time that they can run at that optimum efficiency, and then, yeah, minimising their usage outside of those hours. So it's probably just a high-level explanation of how that system works. There's still some additional benefits, which I'll talk to specifically on the thermal energy storage slide. But yeah, that's essentially how it works. So it's like a centralized heating and cooling system as well. So all heating and cooling in the building is from the 3 heat pump units you can see down there on the bottom of your screen.
And Ross, since we are pretty much out of time, would you like to skip to the thermal energy storage slide?
Sure, yeah. Oh yeah, this was probably the more maybe pertinent slide, but because this was probably the main design consideration we grappled with through the design process. We started off, we nominated low charge ammonia heat pumps, a higher efficiency, and we really wanted to achieve that 0 global warming potential. We didn't want to deal with the synthetic refrigerants. Unfortunately, we have ended up with synthetic refrigerant HFO commercial heat pump in the end. There's a few different pros and cons in favour of each of those different technologies. But if I can put it in a nutshell, at the end of the day, the ammonia heat pumps were too expensive and perhaps just a bit too hot to handle for the engineers, the builder and the engineers that we'd already engaged by at this stage when we got to the all electric decision. A bit more complexity and a bit more sort of unable to be sort of bought off the shelf, so to speak, as the commercial heat pumps are, and there's a bit too much rework into the building envelope required. But look, there are a few benefits in favour of the HFO commercial heat pumps. There's obviously CO2 heat pumps as well, which we didn't really look at in this process. But I'd encourage everyone to continue looking at ammonia industrial heat pumps, because I do expect they'll be the heat pump of the future. They've got ammonia as a zero global warming potential refrigerant, and they can just do a lot more. They're a water-to-water heat pump, and they've got a lot more sort of functionality and innovation that you can utilise in that respect, without going into the detail. But
what do we?
Okay.
Maybe we'll wrap it up there, Ross. And I tend to agree with you that on that ammonia heat pumps. I think that A2EP's opinion, just looking at the economics and energy and the way the heating and cooling profiles needed, we think ammonia definitely worth some more investigation there. Ross, excellent innovation there. Well done, and certainly we know that you're a big part in pushing that innovation forward. Congratulations. This looks like heading towards a fantastic project. And when's that one going to be completed?
In the second half of 2022. Yeah. And as part of the project's funded by ARENA, and as part of that funding, we'll have a live website set up, which will have sort of real-time data that everyone can sort of tap into and have a look. And hopefully, if you needed any more evidence than what's been presented by everyone today, that'll be there as a real-time source of evidence for all the different and various aquatic centre projects that are going on around the country.
Good on you. Well done. A fabulous project. And yeah, we're really watching that one. It's going to be a hell of a benchmark. Congratulations. Good luck with the completion. And I thought we'll just take a couple of minutes here is to do a quick poll while we've got so many people on the webinar. If I can just start this one, just to get a quick snapshot of where people are sitting with heat pumps. If you're able to go to your browser and go to slido.com and type in this number of 791334, that should bring up a questionnaire there for you. Oh, here we go. We've got people opening up already. Thank you. And if we just start off with that first question there and understand where people are coming from today on this webinar, if you complete that first one, that'd be great. So that's slido.com, and in that blue box, you'll see that a number there where you can enter 791334. Got a couple coming in now. Thank you so much. We'll just take a few minutes here. I'm just going to get you shooting from the hip for what your thoughts are on heat pumps, and if you've already had experience with them already, and then we'll be able to capture some really good thoughts about maybe where we could spend some time in the future. I know I've only got a couple of minutes, so we'll have to rush through. The next question is just a quick, simple yes or no. Do you have experience with heat pumps at your council already? From what we understand, we'd probably guess at about 10 to 20% have worked with heat pumps already, but let's see if that works on what we have today. Much, much higher, it seems. There is a really complete missing amount of published information on what councils are using to heat and how much they're using and what have you. But we estimate there's around 100 to 200,000 tonnes per annum of CO2 emissions from aquatic centres, which is an enormous amount. Very good. I'm going to keep on moving just so we can try and finish really close to on time here. Just shooting from the hip there, what's your experience if you were to type in what your experience is with heat pumps? And good, bad, the other. Have you seen corrosion, poor performance, frosting, great performance, energy savings? Not? Feel free to type in what you've seen and we might see some answers coming up there. And this will guide us then for some of the issues that you're having. Freezing, there we go. Certainly from my travels, I've seen plenty of corrosion, plenty of, I'll say, commercial grade heat pumps not meant for the corrosive environment, with powder coated aluminium sides getting some corrosion there. There we go. Good experience there. So quite a mix there. Fantastic. And then if I hit you with a final one, what would you like to see in terms of support? What could we do to help you there? And if we were to design a few more webinars or training programs for you, what would you like to see? Type away. Let us know. And I'll flash my credentials, my emails up after this, and you can certainly email us directly for anything else you would like. Really getting close to time now. Sorry about this, Tanya and Teresa. Awesome. Thank you so much for sending through those answers. So yeah, and feel free if you want to put that through as a question to me. There's my contact details and you'll get that email there. One very final comment before I hand back to Tanya to wrap up is there is options available for heating as a service. We know that CapEx can be an issue. If a heat pump project is that extra several $100,000 more, there is the option to looking as heating as a service, where you pay for kilowatts provided rather than an actual heat pump system itself. Here's a couple of suppliers. You've got Veolia, Flexigen and AirChange are willing to do that and take that on. There's the contact details. You have them there for you as well. I'm going to have to wrap it up there. Sorry, we're over time. Thank you all for the questions, and thanks to our presenters here today. Tanya, can I hand over to you? 1 minute late, my apologies. Local Government Procurement and RDA, many thanks for arranging today, jam-packed. But back to you, Tanya. Thank you.
Oh, thank you, Jared. Look, I'll keep this really, really short, I know, because we've run over time. But thank you, everyone, for attending today. And thank you very much to the presenters for participating and giving up your time and sharing all of your learnings. LGEP is very happy to partner with A2EP and RDA Sydney to bring this webinar to you today, because it is very relevant, given that many councils have carbon reduction strategies and plans in place, and many also have net zero targets now. Aquatic centres are extremely energy intensive, and councils that own and operate these facilities are wanting solutions to improve energy efficiency in order to meet their carbon reduction goals. So we've heard some great council case studies and learnings that we can take away with us today, as well as some technical information on heat pumps themselves and how they work. I'm sure we'll all take away great learnings from today and a greater awareness of this energy efficient solution to explore further, particularly when you combine it with renewable energy. So a summary of the key recommendations and the information from today, along with presentation slides, I'm pretty sure, and a recording of the webinar will be sent through. So we'll get those through to you in the not too distant future. And now, yes, we are very much over time, so I'll let you all go, but thank you very much for attending, and thank you, Jared, for facilitating and pulling together some really great presentations. And everybody enjoy your day.